There are three sections to solar power that we need to be aware of. The difference between solar cells and solar panels, the reasons for seasonal and regional variations in the solar power incident per unit area of the Earth's surface, and then there are problems that need to be solved. So we know that the Sun has a power output of roughly 4 times 10 to the 26 joules per second. The Earth feels some of this power, some of this energy, at a distance of 1.5 times 10 to the 11 meters. The question is, how much energy do we get per square meter on the Earth? This power, which is coming out from the Sun, only some of it is being picked up at the Earth's distance. So there's this radiation coming from the Sun that reaches the Earth. How much of that gets actually to the Earth? Now, we know that the power from the Sun spreads out over the area of a sphere. The area of the sphere is 4 pi r squared, where r is the orbital radius. This is the orbital radius. So any energy that comes out from the Sun is spread over an entire sphere whose radius is the Earth's orbit. So what is intensity at this distance RE? Well, the intensity is that power divided by the total area. So it's going to be power divided by area, which is the solar constant power, divided by 4 pi r squared, which is the area of the sphere with radius equal to the Earth's orbital radius. And when you put those values in, you should end up with a value of roughly 1400 watts per meter squared at the Earth's surface. So if we are at the Earth's surface here, we will get a power of 1400 watts per meter squared. However, this is not for the whole surface of the Earth. Only some of the Earth can receive radiation at a time, not the whole surface area, because the whole surface area is 4 pi r squared. The bit which is on the dark side of the Earth is of course receiving nothing at that time. And 1400 watts is a maximum per unit area. If we're near the North Pole, then it's going to be much less. The beam of light, that beam radiation, is going to be spread over a much larger area, so the power per unit area will be less. So the whole surface is 4 pi r squared, but how much of that is actually getting to the Earth? Obviously not on the far side. The area of the Earth is 4 pi r squared, where r is the radius of the Earth, but the radiation that comes from the Sun is basically only covering pi r squared. So the area of the disk viewed from the Sun is pi r squared. So what is the ratio between 4 pi r squared and pi r squared? Well, of course, this is only a quarter of the total area of the Earth. So you think of the total area of the Earth, but only pi r squared worth of the Earth is actually getting the full power of 1400 watts per meter squared. So the average intensity is going to be 1400 divided by 4, which will be roughly 350 watts per meter squared. This is the average over the Earth during different seasons and during the day and night. We have to distinguish between a photovoltaic cell and a solar heating panel. Now we know the solar constant is 4 times 10 to the 26, with the radius of the Earth is 1.5 times 10 to the 11 meters. So at best, we receive 1400 watts for every square meter. And when you average over the Earth over 24 hours, it ends up being roughly 340 watts per meter squared. So we need to know about photovoltaic cells. Now, sunlight strikes the solar cell and produces a DC current. The energy from the light is able to get an electron to be transferred between the semiconductors, and we get a voltage which is set up. This is due to the photoelectric effect. However, for these solar cells are only 30% efficient, so we need a large area to be able to produce a reasonable amount of power. It's also quite expensive. It is slightly more expensive than having a diesel powered generator when you think of the life expectancy of the solar cell and how much power you can get from it. On the other hand, we have a solar heating panel. This is where sunlight is converted directly into heat, thermal energy. It's fairly cheap and it's quite bulky. People put it on their roofs, for example. So you need a lot of space to be able to basically heat up some cold water. And it's blackened to absorb more energy. Compared with the solar furnace, which is slightly different from the solar heating panel. The idea is the same, but a solar furnace basically heats up the temperature so it's super hot, so you're able to produce steam to drive a turbine. Now, the biggest difference between the photovoltaic cell and the solar heating panel is that the photovoltaic cell basically turns sunlight directly into DC current. This is the only way that we're able to produce current without using steam and a turbine as in a power station. A solar heating panel is not a solar cell. A solar heating panel is a panel which contains cold water which is heated by the sun. Nothing to do with producing electricity. A solar cell has two semiconductors, an N and a P-type semiconductor. When the light falls on this, it basically causes a voltage to be set up between the two semiconductors, usually silicon, and this voltage can be used to drive a current. So you get a current directly from the voltage that's set up due to the photoelectric effect when sunlight falls on the solar cell. We have a problem that you could try to figure out. Your electrical, we need to know how much area of solar cells we need to satisfy your electrical energy needs. Let's think of your family. Let's say there are 4 people in your house. Let's say the average power per person is 10 kilowatts. We know that solar cells are only 30% efficient. We know that on average over the year the power received is 340 watts per meter squared. How much area is needed? Well, let's say we have 4 people, so we need to do 4 times 10 kilowatts, which is 40 kilowatts, 40 joules per second. But the power that we get from that is only 30% efficient, so we need to divide by 30% to realize that we need not 40 kilowatts per family, but 130 kilowatts per family, because a solar cell is only 30% efficient. So we need to produce 130 kilowatts. We know that the power received per meter squared is only 140 watts. So how many of those do we need to make 130 kilowatts? How much area is needed? Well, we know that 1 square meter receives 340 watts, but we need to produce 130,000 watts. So we divide 130,000 by 340, which gives us 382 meters squared per family, which is roughly going to be 100 square meters per person. In other words, 10 meters by 10 meters on average. This is a solar panel. The sunlight shines onto the solar panel. We have a pump which pumps cold water into the solar panel, and then warm water is released from there. And here we have a heat exchanger, so this hot water will heat the water in the boiler. So it produces some of the energy to warm up the water. This is a solar furnace. Here we use sunlight which comes in, reflects off here and focuses on the center here. This will contain a fluid which is superheated, then that can be used to produce steam to drive a turbine to produce electricity. You need to know about the seasonal and regional variations in the solar power incident per unit area of the Earth's surface. You can see that 340-350 watts is these areas here near the tropics. As you get further north, then it becomes much less. We're in Northern Europe, where between between 50 and 150 watts per meter squared. Now we can look at this. You know that the intensity is the power divided by the area. So let's think of these beams of light coming in at different angles to the Earth's surface. Now this beam of light hits directly this area of the Earth, so it's quite a high power per square meter because it meets it at 90 degrees. However, here this light that comes in at a low angle, the same power is spread over a larger area. The intensity is the power divided by area, and if we have a larger area, the intensity is going to be less. So it's going to be less than 1400 watts per meter squared. Also, the sun passes more obliquely through the atmosphere, which means some of the energy will be absorbed by the atmosphere. This also is an interesting graph which shows the insolation, how much sunlight hits different parts of the Earth. Now it's interesting to see that at 0 degrees, which is on the equator, there's a very small variation in the insolation over 24 hours at different times of the year. We're roughly 60 degrees north, so in January we get a low value of insolation, less than 40 watts per meter squared. In the summer, because we're tilted, because of the tilt of the Earth, we're pointing more towards the sun, we get a value of 480 roughly watts per meter squared. And then back to cold winters. So our solar cell would be effective during May, June, July, August, but during January and February, November, December, it's not going to be good. If you take 90 degrees north, which is on the North Pole, there is a great deal of insolation, over 500 watts per meter squared, because the sun is up all day. But then of course we won't talk about the winter time.